Now, I want to point out that there are some very interesting similarities between biological and silicon-based capture of the energy in photons. Both, not surprisingly, rely on interactions between photons and electrons, ultimately. In the case of photosynthesis, which I'm abbreviating PS, those electrons are in the photosynthetic pigments. And in the case of photovoltaics, those electrons are in the semiconducting material that's being used as the basis for the photovoltaic cell. Again, in both cases, those energized electrons are then what are harnessed or harvested. In the case of photosynthesis, they're used to make the intermediates, which then are ultimately used to create the high energy long-term storage compounds, carbohydrates or oils, ultimately. In photovoltaics, you skip the middleman. I mean, it's nice. You go straight to electricity that you can, after inverting it, put on the grid. Or without inverting it, you can use it directly and power whatever DC device you have. And right there, I mean, that is a beautiful thing about photovoltaics, is to the extent that electricity is a wonderful, easily valved, easily transported energy source. PV gives you what you want right there. You know, no offense to all my friends in mechanical engineering, but we don't need your turbines. We don't need to burn anything, right? We just go straight, right? But the problem is, in the case of, let's just talk about biomass to stationary electricity. We're going to burn biomass and spin a turbine and make electricity versus photovoltaic. Clearly, I got to hire a bunch of mechanical engineers to design that power station and to run it. Whereas with the photovoltaics, you know, after I've laid out my hundreds of acres of photovoltaic cells, there it sits. I mean, it's a much, in a way, you know, if I can make a couple of square centimeters and just do that a couple of billion times over, I'm set. It's very repetitive. But I want to make the point that the photosynthetic systems are very complicated, thousands of enzymes, thousands of catalysts, but they're self-regenerating. I mean, I can plant an acre of corn for, what, $100 or something worth of seed, right? What does it cost to put down an acre of PV today? Any idea? It's got to be, I mean, PV is at least, what is it? At least $100 per square meter, round number, and we said 4,000 square meters per acre. So 4,000 times 100, 400 grand, all right? So I might not have to hire all these mechanical engineers to burn my biomass, but I'm paying somebody to make that stuff. So there's this real interesting sort of dichotomy in my mind between those two systems, and I think I think those costs are going to start to converge. And I do think it's entirely possible that 30 years from now somebody has done such a good job with photosynthesis, or who knows, with fusion, that when we look at bioeconomy, we're really talking about using bioeconomy only for a source of carbon to make the built world around us. I could imagine that. But right now, there are some pretty neat things about bio-based fuels, including the energy density that we can get in storage. Electricity is nice if you've got a line connecting you to the place that's generating it. But if you want to store electricity in a car to drive around, the price of electricity storage in batteries is outrageously high. Okay, you're talking a couple of $1,000s to store the equivalent of a gallon of gasoline or a gallon of ethanol. So there are these interesting technological dichotomies between these two pathways.